Thanks for joining our webcast on learning how to overcome common FEA roadblocks. This is the third of 3 sessions, and today we'll focus on making sense of analysis results. Al Robertson from the FEMAP Product Marketing Organization will present, and Andy Haynes, an application engineer for FEMAP, will assist with questions. Just a couple of pointers before we begin. An on-demand version of today's session will be available within about 24 hours from the same link you joined today. You'll get an email when it's ready. Slides from today's presentation are available anytime from your screen. Also posted is a FEMAP customer success story on Aquila Engineering, and we'll be briefly talking about them in the session today. And there's a link to our free FEMAP 45-day free trial also on your screen. If you have any problems with the webcast, click on the help icon on your screen. Sometimes if you just press F5 on your keyboard, that often clears up problems. We'll have a Q&A session near the end of the presentation, but at any time, please enter your questions on your screen in the question box, and that you can do that anytime during the session. So with that, I'm going to hand it over to Al Robertson. Al?
Thank you, Mike, and welcome everyone. As Mike just mentioned, this is a webinar series, Learning How to Overcome Common FEA Roadblocks, and this is the third in a series of 3. And in this webinar, we'll be looking at making sense of analysis results and dealing with the potential roadblocks that comes along in that part of the simulation process. Well, the previous 2, which we ran in June and May, the first one was leveraging your existing CAD data, so right at the very beginning of the process, getting CAD into your FEA environment, and the second one was turning that CAD data into something which could be turned into a finite element model. So this is the third one, and we're going to have a look at dealing with analysis results. Okay, so for an agenda, I'll start off with a brief introduction where we talk at a fairly high level about using FEA, and then we'll go into actually looking at some of the typical roadblocks and how we can overcome them. And they'll be looking at results data files, accessing those, some post-processing tools, and some data manipulation and display. Okay, so let's just remind ourselves about why we use simulation, and this will lead on to some of the factors that really drive successful simulation processes in general. So I guess the principal reason why people adopt simulation is really to be able to perform virtual testing, that is investigating how products behave in a virtual environment rather than going to all the cost and trouble and time taken to build physical prototypes. So principally, we're saving time and money by virtual testing. Failure analysis is also important. It's important to have reliable products that don't fail in the field. Recalls are very costly. They can also damage the company's or the product's reputation as well. So in order to make sure that the products behave reliably in the field, simulation plays an important part there. So saving money is principally the saving there. Optimizing the design is also important, and here we can use simulation to see where there is too much material, or perhaps even, obviously too little material is to be avoided, but where there may be too much material, we can remove some, reduce weight, that reduces cost, saves money. Also, it might be possible to evaluate other types of materials, some less expensive materials, to see if they'll do the job just as well as the more expensive one that's currently being used. So again, saving money there is the benefit with optimization. And trade-off studies too, that's important too. In a virtual environment, it really lends itself to being able to evaluate different designs much more easily than having to construct physical prototypes. So here it really kind of fosters innovation. It lets you try things to see if they're going to work, and that way you can improve designs and save a lot of time doing that as well. So principally, reasons to use simulation tools: saving a lot of time, saving a lot of money, improving the product, making it more reliable. Those are the real benefits from adopting simulation. Okay, let's what are companies doing with simulation these days? This is based on a survey performed by the Aberdeen Group. This is an independent industry analyst, and they sampled a couple of hundred companies, and they got some feedback about their company's objectives and their strategies as far as improving product design is concerned. And overall, the objectives came down to principally reducing development time, improving product quality, and increasing profit. So again, here we have quality, time, and money coming into play here. And some of the strategies, some of the ways that they're doing this, improving product designs, they're analyzing, the best-in-class companies are analyzing product behavior earlier in the design cycle. So again, there's a time factor that's very important coming in there. They're implementing a get-it-right first-time strategy. This is really a remark aimed at reducing physical prototyping. If you can do all the simulation virtually, and then you just need to test it once, and when you test it once, it's right. So that way you can save a lot of time and money. And evaluate more design iterations in the concept design stage. Again, this is a reference to time, to be able to turn simulation around quickly enough so that it sits in step with design, which is really important. So from the reasons to use CAE simulation and what companies are actually doing with it, you can see that time is a crucial factor, and to be able to perform simulations in a timely manner is very important. Just a very brief word about the overview here. Quite simply, I've mentioned this, and this is how our webinar series breaks up. The first webinar series addressed the problems associated with using CAD data, so importing CAD data from a CAD system, bringing it into the FEA environment, and turning it into something that can be used. We identified a few roadblocks in that session, and that's part of the first webinar. And the second one went on to the next part of the process, and that's taking the data and turning it into a finite element model that's actually useful, that will give you the results that you want to get. And then the third one, which is the topic that we're going to be covering today, after the analysis, that's the number crunching part of the process that's done by a solver. We're going to look at bringing the results in and actually being able to post-process and get what we need out of these results, an understanding of the behavior of the model. We need to understand that very quickly, and also to be able to communicate these results to other people. So there are a number of roadblocks that we're going to look at in that part of the process. Okay, so in the sense of this little roadmap here, we're going from analysis to final report, and on the way we're going to encounter some roadblocks, some frequently encountered roadblocks. The first one here is managing large amounts of data. Typically the analysis does produce very large amounts of data, and that can be a problem just to deal with the physical amount of data produced. Second one here, when we're looking at this data, we've got a lot of data that's available. We want to be able to sift through it efficiently and pull out what we need from it very quickly. So limited results viewing tools is another typical roadblock that people encounter. Not having the tools they need to get through all of this vast amount of data efficiently. And then the third one, viewing the results data that's there is one thing, but often you need to turn that data into something else. So you need to manipulate it to some degree, again, to get the actual data that you really need that tells you about the model and helps you communicate it to your customers, and create a report and so on. So the third roadblock that we're going to talk about then is actually manipulating the data that's produced and seeing what we can get out of it even more. Okay, so the three roadblocks then. At this point, I'm going to introduce what we're going to use in terms of a solution, and this is the FEMAP pre- and post-processor. And we're going to see how we can use FEMAP to overcome all of these roadblocks. So FEMAP, just a couple of brief words about FEMAP. It's a standalone FEA pre- and post-processor. That means it does all the modeling capabilities, and that was the subject of the previous two webinars. taking the CAD data, turning it into a finite element model. And it does the post-processing, which we're going to be looking at today. It's a Windows-based tool. It's very high performance. It has very tight integration with the Nastran solvers in particular, but it's an open simulation system. It also talks to all of the major commercial solvers, LS Dyna, Abacus, Ansys, and it's independent of any CAD system as well, which is also important, and it can get CAD data from just about any source. Being Windows-based, it's easy to learn and use. It's a Windows native application, and that means its processes, workflows are intuitive. So just a couple of words about FEMAP, but we're really going to focus on the post-processing aspects. And let's take a look at the first roadblock that we are considering, and this is accessing data results. And just some considerations about accessing data in general. Well, we're seeing the trend these days. The models are getting larger. FE models are getting larger. That's going to create much more data in terms of output from a solver analysis. So the results data is increasing in step with increasing model sizes. Also seeing, people are moving beyond just performing linear static analyses. They're getting into dynamic analyses and dynamic response analyses, in which the data is calculated on a step-by-step basis. If it's a frequency response, it's by frequency, and a transient response is by time steps. So there's a lot more data that's being produced post-processing. Similar for nonlinear approach as well. That tends to be load incremental. So again, data is produced at increments. So with a lot of data to have to deal with, time to access this data increases. And of course, time is one of the crucial aspects that we have to be very aware of when we're performing simulation. And the database sizes can, obviously are going to become very large and can be unwieldy. So in terms of typical challenges that these present, reading in results data, if it's a lot of data, reading it in is going to take a long time. When you come to process, doing all the post-processing in a product like FEMAP, that is going to itself take up some computer resource. It's going to take up some memory. And as I mentioned just now, the database files themselves can become very large and unwieldy to manage. Okay, so what's the solution? Well, we have, in a fairly recent release of FEMAP, a new way of attaching to results. So what you can do is actually import all the results data into the FEMAP database. And as I mentioned before, this increases the FEMAP database size to a very large size if it's a lot of results data. Can take a lot of time to do that. And it really, at the end of that process, you've got a FEMAP database with the results data in it. It's not a very flexible way to access that data. So in a recent release, as I mentioned, there's a way of attaching to the results database. So the results database is actually just sits there, by itself, and FEMAP attaches to it. So there's no importing the results. The database size, it increases slightly because it has to import some address data, which is the blue cylinder that you can see. But that's minimal. The data access is actually faster when it's attached, and you have much more flexibility because the data is sitting there by itself, and you can attach to it. You can actually attach to multiple files, which means that you can have several runs done at different times. If it's the same model, you can bring them into a version of FEMAP and compare across analysis results and models as well. Okay, so let's take shift gears here a wee bit, and let's just take a look at a demo of this.
Prior to analysis, all the modeling data, including all the geometry and finite element model data, reside in the FEMAP ModFem database. When the analysis completes successfully, NX-Nastran creates an OP2 results file that contains all the solver calculated results. In FEMAP versions prior to 11, all results data is automatically imported into the FEMAP database by default. The resulting ModFem actually becomes a little larger than the sum of its parts because of header data required for every load case, time step or frequency value as well as some additional data that FEMAP calculates over and above the solver calculated data, like von Mises stresses. You can imagine that with a transient response performed on a large model, the database can quickly grow to be very cumbersome, taking up a lot of computer resource, including storage space and memory while being accessed. In version 11, you can now opt to attach to external results files instead of importing the data. This significantly increases the efficiency of accessing results data, particularly for analyses like transient response that create results data for many increments or time steps. In testing, we have seen that attaching results files is 6 times faster than importing the results data. The modfem size is also significantly smaller and much less memory is used during results processing. In the user interface, there is a new File menu option, Attach to Results. In the Manage Results dialog, you can see all of the results files that have been attached, with some salient information about the analysis and solver. Here you have additional options to detach the results file or save it to the model database, and in doing so you have full control over which data to save. You can also attach to multiple results files in the same way, which greatly reduces the data burden on the FEMAP modfem file. In addition, external and internal results can coexist. The new method of attaching to results files in FEMAP version 11 offers clear advantages over importing the results data into the modfem database. Attaching is over 6 times faster than importing. The modfem file doesn't become too large and cumbersome, and a lot less memory.
Okay, so just to reiterate a couple of the benefits that we saw in one of the case studies mentioned in the video. For a particular model, it was the attach versus import time was a lot faster, 25 times faster, I beg your pardon. And the opening times were a lot faster as well, opening and reopening times. And you know, the other thing, of course, was that attaching took a lot less memory than actually importing results. So a good way to deal with very large output files is to attach to them. Okay, moving on to the next one, and here we'll look at ways of viewing results and talk about some of the considerations here. Well, we've already mentioned that, you know, potentially we have a vast amount of data to review post-analysis. And we need to be able to do that quickly, so we need to have the tools that show the critical results, the results we really need to see efficiently. We need to have tools that aid comprehension of the behavior of the design under those loading conditions. So again, that comes down to these tools that aid us, give us that comprehension. And also we need to have the ability to communicate, you know, tools that effectively present these findings. So the challenges here then are, once again, the quantity of data that's generated and just sifting through all of that data. Having effective visualization tools, it's very easy to miss some aspect of model behavior which, you know, could drastically affect the design. And also visualization from the point of view of being able to actually get into the model and seeing what you need to see. So you need to blank out some parts, turn some parts, make them invisible, just to be able to see what you need to see. And then, you know, finally, the effective communication of what you find from the results and presenting this to your customers. Okay, well, FEMAP has a real slew of capabilities in this field. Some of them are mentioned here, you know, the obvious ones: deformed shapes, animations, color contours. Also things like free body displays are very important. It gives you a good feel of how the loads are running through the model. Visualization inside the model, dynamic cutting planes and isosurfaces are available inside solid models. You have full control over the output that you select and the output that you view. Grid point force balance is there. And also communication, export of images. FEMAP has a very good way of capturing the screen and exporting it in various forms. And, you know, the last one mentioned on the list is JT. We support JT, which allows you to export the Model Plus results and send that to a third party so they can interactively view it. So a lot of ways of getting the data out and viewing the data. Well, one of the main aspects of post-processing, we have a lot of data. It's spread over a lot of different menus inside the program. We've actually brought all the main output tools that are used and brought them into one place, the post-processing toolbox. So this is a single pane or window inside the user interface, and it really just consolidates all of these options and settings, and you just can go to one place and see them all there. I think we've got a video that demonstrates that. That's coming up next. So once again, let's go and view this video.
The post-processing toolbox can be activated from the icon in the panes toolbar and essentially comprises two main areas covering deform and contour tools. All the controls for setting up the type of plot are there, and full access is provided to the output data, such as all available output vectors. As you make various changes to the post-processing options in the tool, you can elect to have the graphics area update automatically or manually as desired. As you can see, you have full access to all the main options and settings that control the results plot, nodal or elemental, and as these are shell elements, you can select double-sided plots. You can very easily take advantage of any existing groups to help view the results on selected parts of the model as desired. The compactness of the user interface and the efficient way all of the post-processing options are displayed in the post-processing toolbox means that you don't have to remember or know where to find all the settings. This makes it much easier and quicker to set up the results plots that you desire. Besides the plotting options, you also have full access to all the settings for the levels themselves, including the number of levels, continuous color plots, and max-min results display. The same is also true for the legend. You can control its position on the screen, label coloring and display, and the overall size.
Okay, so the post-processing toolbar allowing you to interactively change post-processing settings and so on. Okay, moving on, still on the subject of viewing results, some of the 1D type elements can be a challenge to actually, view results on. FEMAP has a complete set of tools which handles that. Beam cross-sections, first of all, these are line elements essentially, but they do have cross-section data backing behind them as properties, and FEMAP can actually get into that and show the results actually on the cross-section. Furthermore, it can also calculate additional results like von Mises stresses and show them on the cross-section as well. And it has tools to move the cross-section representation up and down. Beam diagrams are also a classic way of reviewing beam post-processing data, so bending and shear force diagrams can be obtained in FEMAP as well. Okay, and we can see that in action. I have a short video here showing that.
Beam elements are a very powerful way of simplifying the modeling of long and slender components in the design. However, as one-dimensional elements, beam visualization can be difficult. For post-processing, many solvers require you to define the points of interest on the cross-section where data will be recovered ahead of the analysis. The trouble is, you don't necessarily know where to expect the highest stresses, and shear distribution details cannot be readily determined or visualized with most programs. FEMAP provides a lot of functionality to help view beam cross-sections and offsets, and beam shear force and bending moment diagrams for post-processing. Now you can also view results on the beam cross-section itself, making it much easier and quicker to gain a full comprehension of beam behavior post-analysis. With FEMAP you can visualize the complete stress distribution and shear flows on beam cross-sections. When visualizing the stresses, you can simply view a single element or specify a selection of elements to include. In addition, You can calculate additional stress output that is not normally included with the output from the solver, such as von Mises stresses. You also have complete control over the force components that are used to calculate the stresses. So you can visualize stresses due to axial loading only, or bending only, or shear only. The forces themselves, axial, shear and bending, can be recovered from any solver. For each element, you can also view multiple cross-section contours, or dynamically move the contoured cross-section up and down the beam for all selected elements. So, viewing results from beam elements, typically the most difficult elements to visualize easily, becomes much easier and quicker in FEMAP with the ability to view contours on beam.
So other tools available, I think I mentioned before, you have a full control over the results selection before analysis, and a full control of results viewing post-analysis as well in the FEMAP user interface. It can show elements. We've seen beam elements shown as 3D entities. Same goes for plate elements. You can show them with the thickness turned on, and it'll linearly interpolate between the top and bottom faces to show you stresses in the middle of the element, so to speak. There's also XY plotting capability, another important method of displaying results. And this is a capability which has been enhanced in a recent release of FEMAP. We have a new charting, an updated charting capability, and I have a video which will give an overview of that.
Charts can be saved in the FEMAP model database, and in this wing model we'll retrieve a chart that has been created previously and continue to work on it. In FEMAP, charting has a fully functional pane in its own right, and through the modern interface you have full access to all chart controls, including line and background colors, labels, fonts, line types, axis formats and scaling, grid lines, tick marks and markers, etc. You can also create and save multiple charts, and display multiple curves in the same chart. Furthermore, all of the charting setup and formatting capabilities are accessible in context with the right mouse button clicking, through the menus or via icons on the top of the pane. The XY plots are based on a series of data taken from the analysis results, and can be filtered down to particular vectors or increment steps for nonlinear transient or frequency results, and displayed for regions or subcomponents of the model. You can set up different groups for different data series, and for incremental data you can set the desired beginning and ending output set. Once the charts have been set up, it's easy to copy and paste them into a Word document to help create a report of the analysis results. FEMAP's charting capability provides a flexible means of creating XY plots with complete control of data, model entity selection and graphical setup. Charting helps you review analysis results and gain insight into the model behavior.
Okay, so let's take a brief look at a case study. This is a company, Australian-based company, Aquila Engineering, work in the aerospace industry, and they're faced with making aircraft modifications. They have to be cost-effective, and there's a lot of they have to meet a lot of regulatory requirements as well. They adopted FEMAP with an ex-Nastran. Some of the keys to success were that data access, which was one of the subjects of an earlier webinar. Compatibility with legacy FEA models, and using these tools they managed to bring about higher productivity. Actually, in the quote there, they actually cite the ability to sift through huge amounts of engineering results data with minimal effort. So that helped to bring them significant cost savings and increased productivity, for their virtual prototyping. Okay, so let's go on and look at the third bottleneck that we discussed, and this is going to the next stage, actually manipulating the results data, the results as calculated by the solver may not have everything you need. So you need to extrapolate or calculate further results in order to get the data in the form that you need to give you the information that you're looking for. So really, you need to be able to do this. Once again, it has to be fast. That's one of the key factors that we identified. For example, to be able to go across a number of different load cases and find the maximum and minima, you need to be able to do things like that very quickly. Comprehension, again, you need to get the data you really need to be able to comprehend how the design is behaving under those load conditions. And once again, be able to communicate. But we mentioned before communicating with your customer. This communication is actually referring to interacting with third-party programs and tools. And we'll see how we can do that. Okay, so these lead to typical challenges. Once again, the quantity of results data generated is a challenge, and just extracting the desired and relevant data can be troublesome. Using effective visualization tools, this is really converting results or calculating additional data to give you what you need. And data access and export, so accessibility and being able to get the data and putting it out to other programs, perhaps for further processing, is also often a requirement. Okay, so FEMAP has a couple of very powerful tools. We're going to talk about free body diagrams. This takes the grid point force data that is produced by the solver and turns it into free body diagrams, which can be for a complete component, for example, for the wing root model you see on the left. Or indeed, you can actually get in and get interface loads between components, and that's what you're looking at on the right here. And visualization, you can see, plays an important role here. You can see that part of the model in this particular image has been turned invisible, making data, this kind of results data easy to look at. Anyway, let's move on. I think we have a video that just gives a brief overview of that. So, free body diagrams.
Free body data is obtained from a number of potential sources, including the grid point force balance results, applied loads, and constraint equation force results. These data requests have to be set up prior to running the analysis. The free body tool streamlines the process of creating force balance and free body diagrams, and is a part of the post-processing toolbox. The free body tool is a separate object and can be stored in the FEMAP database along with the associated calculation options, which means that the displays created by the tool can be reproduced easily. The free body tool is also supported in the API. There are two types of display available, one for free body diagrams only, which is the simplest approach, and the second for interface loads, and which provides more control over the display. There are 6 types of free body loads available, and you can control which will contribute to the free body display by checking or unchecking the appropriate boxes. Let's take a look at the free body first. Elements for the free body can be selected as entities or by group. If we select all elements, we can see for this wing box model the applied loads at the tip and the consequent reaction loads at the root. Now let's take a look at the interface load display. For the interface load display, you can specify the components that will participate in the total summation vector, which provides a force summation and moment calculation for all the nodal summations at a given point. Notice that you can also set up multiple free body displays in FEMAP. In this case, we are going to view the interface shear loads between the spar and the skin in the middle bay of the model. Note that we also pick up a local coordinate system that has already been created to align the loads along the spar cap in that area. We then select the relevant elements for the upper skin and nodes that are positioned along the top of the spar. Regarding the total summation vector, you can opt to leave it placed at the origin or position it in the center of the free body nodes selected. Once FEMAP has created the display, all of the associated data is fully accessible, and you can opt to output it to the messages pane or to the data table. From there, the data can be copied to the clipboard and then into another application such as Microsoft Excel. The Free Body tool also offers extensive control of which vectors, nodal, summation, loads and moments are included in the display, and whether they are shown as components or a resultant. There is also control of vector colors and free body node markers. In View Properties, you can control other attributes, including symbol sizes and vector lengths. So the Free Body tool in FEMAP gives you complete control of free body.
Okay, so another topic to do with manipulating results data, we have results enveloping capability in FEMAP. And this is quite interesting. This allows you to get a single stress plot, for example, of all the worst cases of all the load cases that are in the model and combine them together in one plot. So it gives you a snapshot of the worst thing that's possibly happening to your model due to any load case. And in conjunction with that, also you can get a criteria plot. This is the one on the right here, which is a representation of load set IDs responsible for providing the high stresses, for element by element across the model. So it's a way of seeing exactly, what's happening and what's contributing to it. Now, I mentioned before, there are many different ways of doing things in FEMAP, and this is one way of getting this kind of data. Another one is to use the very powerful data table, and this is, as its name suggests, is a table just for data, and it can be modeling data that you can fire in here, and you have full control over what's in there. I mean, you can highlight some rows and then click the highlighter to see where they are in the model. For example, you can peel off columns. It's very flexible. The way the handling of this data is very flexible. So you can put modeling data in here. You can also put results data in here, which immediately allows you to sort, filter, and evaluate. You can also rank the data, which is again another way of getting through all of the vast amount of data to the salient pieces that you need that show you what's happening with the analysis. And you can copy it to the clipboard and transfer it to third-party programs as well, like Excel and Word, which is also important. So let's go to our final video here, and this just gives you an overview of the data table.
Yeah, a question came up regarding doing results surveys in FEMAP. So I've created the model that was requested. So this is 850 plates, and looks like my math's a little bit off. I ended up with 153 beam elements, but roughly a 1,000 element model ends up being 918 nodes. I wrote a quick API that generated 600 load sets, random nodes just picked with a force. So that's really not a beautiful FEA model from a cool loading standpoint, but they're just random point forces in there, so we can get a big Nastran result set. So I'm going to go ahead and run Nastran now. It's running right here on my laptop, and while it's running, looks like the solve's already complete. It's probably cranking, doing the back substitution to create all the results for those 600 sets. It's done. FEMAP's reading in. I'm actually creating the empty output sets now and reading in the data. So it's getting all the displacements, the stresses, calculating anything that's not there. So here it's doing the calculations and storing it all to the database. So 300, 400, 500, 600, we've got the results. Now the ranking's pretty straightforward. We actually wrote a tool to do this in the last maintenance release of FEMAP. Requires that I bring up the data table. So I'm just going to pop open the FEMAP data table, unlock it. And this is the neat thing. Let's say the first thing we want to do is just find the max von Mises stresses for the plates. We have this list output results ranking to data table. And I'll just take the defaults here just so we can, and there's some options in here depending on how you want to do this, but we're just going to grab the top 5 max value. You can multi-select. Here's all my 600 output sets. I can just box pick across them and toggle them all on. And then come down here in my output vectors and find top von Mises stresses. And then include similar. So this will go get bottom von Mises, and I'll get the corners too. So in one shot here, we're going to go grab all the maximum von Mises stresses for, and it's asking me what elements to pick, and I can just say by type. And go pick one plate out of the model and just say more. Just make sure we're getting them. There's all our plates. Say OK. It's cranking through all 600 sets for 850 elements. There, the data is already in. So here's my data by set ID right now. It's subdivided as we told it to. But so within each set now, I'm getting my top 5 von Mises stresses. I could just pop this over to Excel with a copy. Or also a neat thing we can do here is let's just bring this back in, and now it's not even subdivided by set. I can now just go right up and down here and just say I can find my top von Mises stresses instantly for the entire thing and see that it's element 629 in this set ID, so for load set 418. And I can actually turn on the highlighter here and have FEMAP show me who element 629 is. So, oh no, it looks like it's probably that's the rank is coming out there, so it's not showing it to me. But window, show entities, element 629. So there's my worst von Mises stress, and I know it comes from output set 418. So then we could go in here and just take a look at that. Let's change this to 418. It's got von Mises stresses. Say OK. And there's our picture. Must have that little load right there. So ranking is pretty easy and pretty straightforward.
Okay, so in today's webinar, we've identified 3 common roadblocks, and we've gone through and looked at those in a little more, each of those in a little more detail. And the first one we considered, just the problems managing large amounts of data. And we saw how FEMAP has now the sufficient results database attachment method, which speeds up the whole data access and also reduces the amount of computer resources that are used in post-processing actions. The second one we looked at was actually results viewing tools and how we need to have a wide variety of those to be able to get the information that we're looking for. And we just looked at a few that are in FEMAP. It's FEMAP has an extensive set of results viewing capabilities, and we really just, barely scratched the surface today. But there's a lot of good functionality, and that helps to reduce the post-processing time. And the third roadblock was really to go, to the next stage, and just beyond the data that's presented to us, to be able to manipulate the data that we've been given from, from the solver, and actually manipulate it to get it in a form that gives us more information, information we really need. And we've seen a couple of capabilities in FEMAP that help us do that, and also that help us connect with third-party products like Word to create the final reports, and Excel, maybe for further processing, and so on. So that clears the way between going from the analysis then right through results viewing to the final report. You can use FEMAP to clear away all of these roadblocks. Okay, so back to the key point that we mentioned right at the very beginning. The reason we need to do this, of course, is to maintain a fast turnaround time from the simulation point. This is key to keep in step with design, to make sure that the development time is as short as possible. That's one of the key things that best-in-class companies are striving to do, one of their objectives that we talked about. To also speed time to market is the other important aspect too. Okay, well, we focused on just one aspect of the simulation process today, post-processing. I introduced FEMAP earlier in the presentation. Just a quick return to that. You know, we haven't seen everything that FEMAP can do in this presentation by any means, but you know, just the main points again. You know, FEMAP is a pre and post processor. It handles all the modeling aspects as well as the post processing that we've seen today. It's standalone, so it's independent of CAD, though it can access CAD from just about any source. It's independent of the solver, obviously, as a pre and post, but it can access all. You know, it can send data to and look at results from all the major commercial solvers, but it has a particularly high degree of integration with the Nastran solvers. And being Windows native, that makes it more intuitive to use and quicker to learn and reduce training overhead. Okay, well, those are the general aspects. One other thing I should mention about FEMAP is the application programming interface. This is very, very powerful. This really allows you access to all the FEMAP capabilities actually inside the program, and you can use that to automate various aspects of the simulation process. Or indeed, if you have your own solution which builds upon what FEMAP can do, then you can actually integrate your solution completely, entirely inside the FEMAP environment through the API. And we've seen companies do this with things like fatigue solvers and composite layup modelers and things like that. Okay, well, this is the third in a series of 3. We did have the previous 2 that we ran in the previous months, as I mentioned. We do have recordings for the first 2 if you missed them. So if you just go to the link that you went to today, you can actually browse through and get to links for the other 2 there as well. The recording for today's will be made available in a couple of days once we get it actually finished and uploaded to the site. So you can go back and review these if you like. A couple of other points to make. If you want to get more information about FEMAP, there's certainly a lot on the FEMAP website, which you can simply get to by typing femap.com. That'll take you to the Siemens PLM website, the FEMAP part of it. Also, I should mention that there's also a 45-day trial available. This is completely free. You get the full FEMAP program plus NX Nastran with the dynamic modules and optimization modules as well. So you can download this. The licenses are sent to you electronically, so there's no interaction with anybody. You can just go to the website and get this and try it for yourself for 45 days. Try it out in your data sets. FEMAP does come with a full online help system, which is also part of this, and there are many tutorials that will guide you through using FEMAP. So find out more, download the trial. And I think that brings us to the questions and answers. So thanks for your attention, and if you have any questions, we'll be glad to answer them now. And I have my colleague Andy Haynes with me here today as well.
If there are no questions on the line, we do have a few that came in online that we'd like to answer. Someone asked, just as from a CAD data standpoint, if we can import geometry from SolidWorks. Yes, the answer is yes, we can do that. We can import parts and assemblies from SolidWorks. We can also, FEMAP can import several different kinds of more generalized CAD data, such as Parasolid, ACES, IGES, and STEP files. So I hope that answers that question. Someone else asked a question if they said they're not a 3D CAD user, and when they saw the beam and the shear moment diagrams, asked if we could create any sort of section in FEMAP. And I believe what they were talking about was any sort of beam cross-section for a 1D element. Yes, and the answer to that is yes. We have a full library full of section types like I-beams, C-channels, angle brackets, etc., where you just enter in your various sizes, thicknesses, etc., and then you use just two positions in space to represent the length of a beam. And so yes, we can certainly do that beam modeling in FEMAP. And what you saw in Al's presentation was a little bit about the way that we can post-process those results, which was with shear moment diagrams as well as with the actual showing stress on the beam cross sections as well. Does anybody have a question on the phone? No? Okay. Wanted to highlight again, too, that someone asked if we can import results files. Yes, the answer to that is yes, we can certainly do that. Again, with the attachment of results files, that had more to do with people wanting to attach a large, very large amounts of output data to FEMAP. And that's where Al showed you all that, just the great performance improvements that you could see from attaching instead of importing very large results files. But FEMAP has always been able to import results, and we'll basically always be able to do that moving forward. Someone asked also about optimization tools in FEMAP. Right now, what you can do is we have the ability to use Solution 200 in NX Nastran and MSE Nastran for that matter, and that is a size optimization. Doing shape and topology optimization is certainly something that is better handled through a third-party product. I'm going to look through some of these other questions that we've gotten. Here's one that just asks, can we compare two FEA models which have minor differences? The answer to that is yes, we can do that through the data table. We can also do that through just being able to create and list out output from each different model one at a time, and then compare it. So I hope that kind of answers that question. The nice part about using the data table is what you can do is you can actually list the different outputs from the first model and the second model, then even turn on just a specific model ID column in FEMAP, and then actually sort that by the actual element ID or say node ID or anything of that nature, and just so you can see a comparison right in like in our data table, which essentially looks a lot like an Excel spreadsheet. Again, I'm just going to look through some more of these. We just got quite a few more.
We will be answering these actually by email too. So if we don't get to your question today, we'll still provide an answer.
Someone asked if we have a 3D visualization. We actually used to. That has actually been removed from the program. So no, there's no thing where you can put on a special set of glasses anymore and see FEMAP in 3 dimensions. Just wanted to highlight that. Oh, this one actually appears to come from a FEMAP, a current FEMAP user. They just wanted to know what output settings do they need to do to have results not import and attach. What you're going to want to do is go to File Preferences, go to the New Results tab in FEMAP 11 or 11.0.1, and there's an option in there to automatically attach results when you import results. Okay? going to take a look here. All right, yeah, there's actually quite a few questions for me to go through, so maybe we should just take some extra time and answer these up a little later with email answers.
Okay, thanks, Andy.
Mm-hmm.
Okay, so I guess with that we'll conclude today's webinar. Once again, thanks for your attention, everybody, and we have a lot of response in terms of questions too, so thanks for that. And we'll be getting back in touch with answers to these questions. And by all means, please go ahead and download the 45-day trial and give FEMAP a try. Thank you very much.